In this video, we're going to talk about a two-step test for determining whether a subset of a ring is a subring. So, just as a reminder, we have R a ring. So R is a set with two operations, addition and multiplication, satisfying all of those lovely properties we talked about. And we're going to assume S is a non-empty subset of R. And the theorem here says that if S satisfies both of these properties, then S is going to be a subring of R. Notice that there's actually really three steps here, because in order to show S is a subring, we would have to prove that this condition holds, and also show S is non-empty. But usually the non-empty part is not too hard to show. Okay, so a couple of bits of terminology here before we get started. We introduced this in a previous video, but I just want to mention again, a subring is a subset of a ring R that is itself a ring. So itself, it satisfies all of the properties of a ring. So that's what a subring is. And there's also this expression x minus y. We haven't talked about this yet, but we define for x and y in a ring, we define x minus y to mean x plus the opposite of y. And that's our definition of subtraction. In grade school, we have different definitions of subtraction, like taking away or finding a missing addend. And in abstract algebra, just to avoid trouble, we define subtraction in one way, and that is subtracting y is the same as adding the opposite, just like you learned in probably 6th or 7th or 8th grade when you learned to add and subtract negative numbers. All right, so anyway, here's the proof. This is the proof of the two-step subring test. So let's assume everything above. Assume R is a ring, S is a subset of R, S is non-empty, and S satisfies conditions 1 and 2. We're going to prove S is a ring. All right, so to prove S is a ring, we have to show that it has all of those properties that we promised a ring ought to have. And I believe there were like 8 of those. So the things that we need to prove are, number 1, we need to prove S is closed under addition. We need to prove that addition is associative. We need to prove there's an additive identity. We need to prove there are additive inverses. We need to prove addition is commutative. We need to prove that S is closed under multiplication. We need to prove that multiplication is associative. And finally, we need to prove the distributive properties, both of them, the one on the left and the one on the right. But before we start a proof that splits into 8 steps and start going, oh, step 1, step 2, step 3, let's just give ourselves credit for the ones that we know are going to be true. Because there are some of these that, honestly, we already know. For example, we are given by condition 2 that S is closed under multiplication. So let's not set up a proof for that. Let's just say, look, we know that. That's condition 2. Okay. What else do we know? Just by inheritance of properties of operations from the ring R, we know that addition is already associative. It's not going to stop being associative just because we're looking at a subring. It's still going to be the case that for every x, y, and z in S, we have x plus y plus z equals x plus y plus z, because those were all elements of R, and associativity was true for all elements of R. Similarly, we know that multiplication is still going to be associative. We still know we're going to have a distributive property, in fact, both of them, because those properties were true for R, everything in R, so they're still true for everything in S. We know that addition is commutative. I know I'm going in sort of random order, sorry about that. So the things that we need to prove S is closed under addition. We don't have a condition in our hypothesis that directly gives us that. We have something that indirectly gives us that. We need to prove there's an additive identity. We need to prove there are additive inverses. And I think that's about it. We don't need to directly prove anything about multiplication. We pretty much assumed everything we needed there. All right, so let's zoom out. And let's get to work. I'm just going to move this over a little bit so that we can see the proof over on the right side of the screen. Okay, so here's the proof of those three missing parts. Let's start with the additive identity part. To prove S has an additive identity, and in fact should have the same additive identity that R has. Since S is not empty, let X be some element of S, any element of S. Then, by condition 1, we know that X minus X also belongs to S. S is closed under subtraction of any two elements of S, even the same element of S. Well, X minus X, by definition, is X plus negative X, which is 0. That's the 0 of the ring R. So that additive identity does belong to S. Because it's an additive identity for R, it's also going to act as an additive identity for S. So S contains an additive identity. Super. We are on our way here. All right. Now I'm going to prove that S has additive inverses. I realize I'm going in a sort of weird order here, but I'm going in an order strategically that I think is going to help me to complete the proof as efficiently as possible. All right, so to prove S has additive inverses, let's let X belong to S. We'll prove that the opposite of X belongs to S. Well, if we know that S is closed under subtraction, and we know that S contains the additive identity, then if I use the subtraction property very skillfully and strategically, I shouldn't have much trouble proving that opposite of X belongs to S. Here's what I'm going to do. Since 0 and X both belong to S, 0 is the additive identity from R, we know 0 minus X, which is the same as 0 plus opposite of X, belongs to S. But of course, 0 plus the opposite of X, since 0 is an additive identity, is just the opposite of X. So the opposite of X belongs to S. So we know S has the additive inverse of each element of itself. And finally, to prove S is closed under addition, let's assume X and Y both belong to S. I want to show X plus Y belongs to S. Well, how am I going to get X plus Y if I know S is closed under subtraction? Well, I need to think about how to get X plus Y as the result of a subtraction problem. Well, how do I get X plus Y by subtracting? Well, I could subtract X minus the opposite of Y. And that's why I'm doing the properties in this order, is because now I have additive inverses. So we also know opposite of Y belongs to S. So by condition 1, we know X minus opposite of Y belongs to S. So I claim X plus Y belongs to S. But now I realize one thing. I haven't shown yet that X minus the opposite of Y is X plus Y. That seems like a little bit of a reach, because the definition is X minus negative Y is the same as X plus the opposite of Y. So let me write this down. So Y is X minus the opposite of Y equal to X plus Y. By definition, we have X minus the opposite of Y equal to X plus the opposite of Y. So we need that opposite of Y to equal Y. But to show that that's true, I can just do the following little mental stunt here. I can say that I know that the opposite of Y plus the opposite of the Y has to equal 0, because I'm taking some element of the ring, which by the ring I'm referring to R. I haven't totally proven S is a subring yet. I have if I believe that all of this is true. But I'm taking an element of R, and I'm adding its opposite. That should give me 0. But also, if I write down negative Y plus Y, that would also give me 0, because this represents the opposite of Y. Adding Y to its opposite should give me 0. So these two expressions are the same. So moving up just a little bit more, this tells me that opposite of y plus opposite opposite y is the same as opposite y plus y. But under addition, R is an abelian group. I can cancel things. Cancellation is something I can use in abelian groups. I can use in any group. I can cancel on the left, and therefore get opposite of y equals y by left cancellation from groups. So here we're using a little property from group theory to help us with a ring theory proof. Okay, so anyway, that proves that the opposite of y is y. That completes this proof here. That shows that x plus y is a element of S, and therefore I think S now qualifies. It satisfies all 8 properties of a ring. So I can say S is a subring of R. Huzzah! So what this means, let me zoom out one more time here. What this means is that if I have a ring and I have a subset that I know is non-empty, remember I use the non-empty property right here to let X be an element of S, because technically the empty set satisfies both of these conditions, but the empty set would not be a subring. So that non-empty part is really important. But if I know that S is a subset of a ring R, non-empty, it is closed under subtraction and closed under multiplication, I will know it's a subring. So from now on, anytime I want to prove something is a subring, all I have to do is establish that it's non-empty, establish it's closed under subtraction, establish that it's closed under multiplication. And at that point, all of the other properties of a ring follow.